Hello, everyone. Thank you for joining the ISDSA workshops. Today, we are very fortunate to have two outstanding researchers, Dr. Xiwei He and Dr. Susu Zhang, speaking on analytic methods for process data in large-scale assessments. Dr. Xiwei He is an associate professor in the Data Science and Analytics program at Georgetown University, and she is the founder and director of the AI Measurement and Data Science Lab. Her research focuses on advancing methodologies in sequence mining, text mining, psychometric modeling, and machine learning on new data sources, such as process data and textual data, collected in digital-based assessments in education, psychology, psychiatry, and public health. She was an OECD Thomas Alexander Research Fellow and the recipient of NCME Annual Award, Jason Millman Award, and the Alicia Kaskela Award for her contribution to developing and applying new methods in process data analysis. Our last speaker, Dr. Susu Zhang, is an assistant professor of psychology and statistics at the University of Illinois, Urbana-Champaign. Her research involves latent variable modeling for testing and learning data and the analysis of complex process data to inform educational measurements. She has contributed to several packages for psychometrics, and she is the recipient of the NCME Alicia Kaskela Award for her outstanding work in integrating process data into psychometric models. So during the session, if you have any questions, please feel free to drop them in the chat as we go. And now I'd like to turn it over to our speakers. Thank you very much.
Yeah, thank you very much, Zhong, for the introduction and also invite us to give this workshop at ISDAS conference. So that is an annual meeting for the International Society of Data Science and Analytics. So it's our great honor for Susu and I. So we share what kind of we learned in the process data and hopefully to have some inspiration for your study as well. But if you have any questions, please feel free to put into the chat. And also, if we cannot really capture that at the same time when we give the lectures, and we can catch them up later. Zhong, do you want to take the recording or not necessary? So
I think it's being recorded.
it's already being recorded. Thank you. Yeah. So just now, actually, Zhong already gave a very good introduction for me and for Susu. So you can see I propose a distinguished associate professor of data science and analytics in Georgetown University, located in Washington, D.C. So data science and also the process data learning actually has been a kind of a great topic for my research for over 10 years. And before I joining the Georgetown University, actually, I spent over 9 years in ETS especially for the large scale assessment for PISA, PIAC, and NAEP. And so you can see actually today we were sharing this kind of working experience actually is also from the experience from at ETS and also some new things actually we develop now at the university. So we have a lab named AI Measurement and Data Science Lab. So there are many students actually work together with us. So it's a great experience actually to work on the process data. And thank you so much for joining us and also to have interest in the process data. And also, I think just now also Zhong also gave a very good introduction for Susu. So I also put Susu over there, and Susu actually is working quite a lot things for the latent variable modeling and also focus on the process data and also psychometric modeling to combine these kind of things together into the measurement. And especially her contribution in the analysis of the NAEP mathematical process data to understand the performance gap between learners from different demographic variables, for example, for the students with special needs and also with the normal students and what's the differences and how we can use the process data actually better to serve this special group people and understand what their strategy and what their behavior and get this kind of insights and to support the teachers and also the assessment developers. You can see actually Susu is also a very productive scholar, and she has already published quite a lot of papers in this kind of way, and also got a great honor from NCME as 2022 Alicia Kaskala Award. So it's a very good honor we collaborate together and to give the workshop today. So we can see the schedule today. Actually, altogether we'll have 3 hours. We're starting from 5 o'clock, and so now it's a kind of introduction for ourselves. But actually, it's yeah, if it is in person, so we can invite all the participants actually give the introduction for yourself. But I think it's a little bit hard actually when we come into the Zoom online. But it's totally fine, and we will start to have the section 1, so that's the sequence-based methods of process data analysis, and especially with the case studies in the PIAC data set, because you can see actually process data is kind of a new data source, and with a different format from the sequence base. So it's kind of a new things actually that will be interesting to go inside and to explore this kind of new data. And after that, we'll have a short break, like a 15 minutes break. And after that, Susu will come inside and to give the feature-based methods for process data analysis with a case study, especially in the NAPE dataset. Because we can see the process actually, even though that is in the format of the sequence, but actually we can extract quite a lot of new information from inside. And all this kind of new information can be grouped them into the variables, either from observed variables or come into the latent variables. So Susu can actually, and her work actually do quite a lot from this kind of feature-based methods, and to see how we can use them together with the response data and to work analysis on the large-scale assessment. And we reserve 10 minutes finally, and to give the open questions and to discuss about the future research. So please feel free to put your insights, put your suggestions or thoughts or input into the chat, so we can have some for the analysis, for the discussion on them. Yeah. So any questions, please just put into the chat, and I think Zoom can help us to coordinate that. Okay, so I think that is a good time, so we can come into the section 1 now. Let me share my screen into the section 1. Yeah. So in section 1, I will focus on the sequence-based methods from process data analysis. As just now I mentioned for this kind of new process data, new data source, and we want to find some tools and methodology actually to work on this kind of new data. And so the very important thing is we get understanding about how this kind of sequence data look like and how we can use them to our analysis. So before we come really into this kind of sequence-based methods, so let's come into a kind of a general picture about the test. So we can see actually for the test, it's already been 1,500 years of the history, right? So you can see actually on the left-hand side, so this one actually you can see that is the first time of the test from the empirical Sui dynasty actually in China. So that is the first time when we have the test, even though at that time actually is the emperor is the final judger or final evaluator for the people, for the participants actually to submit their essay. So they write their essay, and then we have the human rater to rate them and then make a final decision. So you can see, even though that is relatively subjective, but we have this kind of test at the very beginning to have this kind of form and use that to make a selection. And the second picture actually shows for, this is the first time when we have the high school students take the first ever National Merit Scholarship program exam. So that is in 1973. So you can see actually at that time, so people is not only to use this kind of subjective essay writing, but they come into the more standardized way. So they can have multiple choice questions, and they can have quite a lot of different forms or types of the test. So you can see at that time, of course, that is only based on the paper-based exam, paper pencil exam. And we can see actually, so the history continues to see the modern theories in measurement with a tremendous data source are rapidly transforming the testing from unaccompanied data measures into informative tools that can be used to address the various challenges in today's teaching, learning, and assessment. So that is a sentence from the past president of International Psychometric Society, from Professor Hua Chang. So you can see actually now we can have this kind of test into the computer base. So especially starting from the beginning of 2000, and more this kind of computer-based assessment come into life. But nobody knows what will happen in the future. For example, this picture actually shows kids actually use this kind of VR. So VR now is kind of a toys actually for the kids to play and to learn, but nobody knows what will happen in the future, whether that will come into a kind of assessment tool, right? So because we have this kind of tremendous source, and not only this kind of final product data we can capture, but also all this kind of process we can capture them. And you can see, give a quite concrete example to say when we have the PISA data set. And PISA 2012, that's the first time when we have the test come into the computer based. So we assume that at that time we'll have 45 countries join the test, and each country will have 5,000 students as a representative sample. And we have 100 items for each student. So why we have 100, so that means generally PISA test, we will have the math, science, and reading, and students also need to do the background questionnaires. So we just assume each student will answer 100 items. And altogether, we can have 22.5 million the data we can capture from this big test. So that is in PISA 2012. So when we first time come into the computer-based assessment. And when we come into the PISA 2022, so that is actually the 90 countries will join the test. And we assume each country still have 5,000 as the student sample. And they still answer 100 items. But you can see at that time, actually, we can capture their transition, navigation, the timing point. So we'll assume that we have the 10 transitions and 20 of the actions and time point per item. So you can see actually the data set becomes much, much larger, right? Becomes 9,000 million. So between the 2012 and come into 2022, within 1 decade, within 10 years, we can see actually the data size enlarged by 400 times. So all these kind of new things actually will be just showing up there to have this kind of big data from one test, from one PISA, this kind of test. And also at the same time, not only for their data set becoming enlarged, but at the same time, we also have these kind of examples from different subjects. So you can see actually we have new innovative item design as well for that. So this kind of a new item design actually support the new items, new data we can capture them, right? For the first one, actually, you can see that is PISA 2022. We have the creative thinking. That is example item. So in that one, students will click on different icons and put them into a simulation based environment. And so at that time, actually, students will create their own posters, actually for this kind of astronomy event. So you can see actually students put in and put back, and also they will write down, make an interpretation about their poster. So all this kind of feature and also data we can capture from this process. So you see that actually is kind of process we can include a rich information insight. And second one is from the team's 2019 scientific problem solving and inquiry example item. So for this one, students actually come into a kind of a real experimental design. So they need to figure out to say how much water, fertilizer, and also the sunlight to give this kind of plants. And the last one is for the math example item. For example, like this item, a student need to figure out what's the statistic from the proportion probability over there. So for example, student can spin that and to get a kind of a probability running, and also by different scale. So each time they can have a kind of entry. And so for the entry, actually students can see what kind of entry they get, and based on their repetitive this kind of experiment and also exploration, they can get their final answers and put that final answer into the box. So you see, actually now we have quite a lot of this interactive design for the item. So these kind of items actually will also help us to produce the big data. So the big data from the process, actually that will be something we want to capture. So we can see actually the practical sequence log. So it's similar like when we have our daily life and in our just in the life, for example, like that, we have a kind of bucket of cherries. We want to say that's kind of a correct results at the final, and we want to capture to see how this little guy actually get this kind of cherries. So you see, the first time the little guy just sit on the shoulder of his father, and then to find some cherries over there and to get the cherry, and then come to the next one. Oh, he finds there are some cherry just by his hand. He can directly get them, and he put his cherries into bucket, and then he finds there are some cherries actually he can stand on his toe and to reach that. So capture the cherry and put all the things in his bucket and back home. So if we get this kind of bucket of cherries and we want to go back and to see track back to see what can happen to this little guy, and also we can find during this process which part actually the students need to have the help or a kind of intervention to support them. For example, he need to sit on the dad's shoulder and to find this the cherries, and also sometimes they can easy to get it, and also it is challenging, but students can persistent to get it. For example, he stand on his toe and to find this kind of solution. So it's similar like our daily life. The process data help us to capture this kind of information and to support us in the platform and to get it. And we can see actually the example process data collection. So assume that is we have the PIAC item design. So you can see on your left hand side, so we have the PIAC, this kind of item. So students come inside and they will click on different buttons to make a exploration. And during their exploration, we can capture their actions and also time point. And based on the action, that is event, and also the time, we can also calculate the interval between each actions. It was showing up this kind of transform this kind of structuralized data. But before that, actually, that is relatively messy. It's a kind of a HTML file. We got the data. It actually is not that a structured way. But here, when we have the structured way, and we can see, we can start to calculate the start and with the interval time, and to see at which time and which data point actually we can capture what kind of event over here. So it's a kind of a process data come into our process, and also assessment process all together with our response data. So here actually we want to see a typical assessing process that could be. You can see actually before, if we only come into the paper pencil test, and we could have a kind of things in between as a kind of black box, because we don't know what is happening over there if we do not capture this kind of data. So you can see based on the standardized test or the item response theory, this kind of theory-based testing or measurement, we can find actually students' final the results of task completion will contribute from the person level characteristics and also task level characteristic from these two perspectives. So from our person level perspective, basically we will have the students, their demographic variables, personality variables, speed, motivation. So you can see actually we generally put this kind of part into the covariates and to describe how the respondents is working on that. But at the same time, we also have to consider about this task level. So task level generally will have, like to say, item type, item format, item difficulty, item position, and item wording. So these kind of items actually will give us different parameters there. For example, like difficulty parameter, discrimination parameter, and also consider about whether that is multiple choice items or open-ended questions. So you can see actually where the item is located at the beginning of the test or to the end of the test. For example, that will have a differences between the engagement or their time and time allocation for the students. So all this kind of information actually basically we base on these kind of items, and we got the student response. And also based on their demographic variables, and then we can calculate to say what kind of results of task completion over there. But now becomes into the computer base, actually we can have more information in their completion process. So the black box becomes white, so we can know better around this kind of completion process. And then if we want to go deeper to see what is happening in this black box, a kind of a completion process. So we can come in to say, basically we will have our basically we'll have observed variable as a y, so that is response data. And so the response data actually can represent our theta value. So that is the theta from the student's latent ability. So that is our interest about to say how we can estimate that. So that is we will use the y to represent our theta and to get the latent estimation of that. But currently, when we have more information from the process, actually that is non-ignorable, this kind of new information. So you can see the new information located over here to say not only the y, but also the yp, we want to capture them. So the yp is the process data, and to see, okay, not only from their product, but also we have the process. And also the yp can also represent their latent trait, so that's the theta. So you can see actually the yp is observed because that is from the log file. And that one represents partial of your theta. And also yp can have this kind of interaction with the y to say, because you have this kind of process, so that could impact your y to say final response. And also in other way around to say, when you have this kind of selection on what kind of responses finally, and then we can track back to see how you can work on that. So that is an enormous amount of unstructured data is collected, so from both performed actions and associated timestamps. So the new data source not only for debugging as a byproduct, but provide a comprehensive profile for the test takers. You can see actually this kind of process data before when we design items. So basically they just stay over there as a kind of byproduct, and we want to use them when we need to debugging where's wrong, what is kind of things wrong with the student or the item. But now actually besides on that kind of technical support, and we also find very rich information in that kind of data. So this kind of new data, as we explained at the beginning, to say that calls for new methods to incorporate data science and analytics techniques to reshape the future of assessment or the measurement. So that is because not only the Y, but also we have the YP to include in them, and to see how we can analyze this YP and to get a better estimation for the theta. I think Susu later on will use this kind of things and actually to introduce about how we can use the process data to strengthen the reliability and the validity this kind of way. So you can see actually YP and Y, they just observed over there, and this kind of new things, and we want to have some data analysis method, analytics methods to handle this new data source. Yeah, here we summarize to say, why does the response process matter? It can have 5 perspectives to show its importance. So we will say the task construction is the first one, because when we use the process data, and actually that can contribute a lot to the task development. So for example, when we investigate if examinees interact with the task as intended. So that is very important, because sometimes the item developers, they develop their items and they think, okay, that is good items. When the students come in, and then they can figure out to say they can solve the items, and not necessary to follow your path or your solution, but they still can get correct answer. Or the students can be very creative. Actually, they can give you totally different ways to do that. But sometimes you also can see, you think that is quite easy item, but actually for the students, they will see that is more complex than you expected. So this kind of process data actually can help us to make a tool, as a kind of tool to check, to see whether the students are really work on the ways that you expect them to do, or otherwise you want to make some adjustment, especially when we have this kind of data analysis on the field trial or pilot study. You can use them actually to figure out to say what is wrong with the data, with the item over there. So the second aspect of what we say is for invariance explorations. So especially for defining invariance between the group, not only by the item difficulty, for example, we can check for diff, but also the problem solving process and strategies. And for example, so for one country or for one group, actually specifically, they will use some strategies totally different from the others. So that could could arouse your attention actually, for example. For example, when we do the PISA test, we find that Singapore students generally will be always showing different behavior patterns than the other students when they do the navigation. So it's a kind of instruction differences for the students. It will showing up, reflect into the invariance explorations over here to say what kind of things when we compare between different countries, they will show these kind of different things. And of course, when we have the more data, we can have the more richer descriptions. So for instance, we will have investigating if examinees could solve a given task and how efficient they did. So students who answer one question by 1 minute, that would be different for the students actually answer the same question and same answer by using 10 minutes. Right, so for their differences over there and their strategy actually can tell us quite a lot of things about students' cognitive process. And so the new data can actually also help us to refine the theories to see what kind of theories we can learn from them. So providing the evidence for cognitive process that could not be captured from paper pencil-based assessment. So the last one is the tailored interventions. Yeah, when we have this kind of process data, we capture their personalized things, right? Their strategies, their time, whether they're fast speeder or the slow test takers. So you can have this kind of personal things from the respondent. So that actually can give us a kind of a good profile for the students in a more comprehensive way. So that is identifying sub-skills or meta competencies that examinees are lacking or really good at. So based on this kind of a general picture about overview of the process data, and then we can continue come into specific methodology to say what kind of methods actually we can really use to handle this unstructured, multidimensional sequence data. So the sequence data actually would be very good when we come into the sequence mining. So the sequence mining methods in process data actually can help us doing quite a lot of things and to capture the new information and also to explore the patterns from the students' their behavior. And also we find when we have the text and the click streams, actually, the click streams, that is the students when they do the actions and also have the time point, they are commonly encountered types of unstructured sequence data, which facilitates a borrowing from text mining, natural language processing, and even currently we have a large language model, and the diversity of machine learning methods over here. So let's see some concrete methods that we can use for the sequential process data. So the first one, call them as a mini sequence. We also call them as n-grams. So that is a disassembling long sequence into manageable short pieces. So for example, when you have a very long sequence of the students when they solved one item, that will be quite hard or challenging to directly to use the whole sequence. So at that time, you want to chunk them into small pieces to say we have a long one and we'll chunk them to small pieces. And each small piece will become a kind of feature in the students' their behavior and also strategy. And based on the small chunk, the small pieces, that will be more manageable and to do all the analysis. And the second perspective, when we use a sequence, that is we use a sequence of proximity measures to calculate the distance between the sequences to see they're similar or dissimilar to each other. So this time we will not chunk the long sequence into small pieces, but actually we will use them as a whole and compute the distance between each pair to create new variables. To see, that is actually the first step. You want to calculate the distance between the sequences. And after you calculate them, you can get a kind of a variables. And so the new variables actually can make a kind of a generalized across the different items. The third one, generally we'll call them as latent sequence modeling. So from observe the sequences to derive the latent sequence transition stage and the probability. So that means the students actually, you can observe all sequences there. And based on their sequence, you want to see what kind of a latent trait or latent sequence they can get. That is from what kind of state transition to the other one, and how much is the probability during the transition, and how much actually we can represent from the emission probability there. And the last one is called the large language model. So that is quite popular now, actually use large language model, especially from the ChatGPT or the other kind of generative AI tools, and come into the sequence things. So large language model, that is kind of a new trial for us. And we can share something about this kind of self-trained mode from sequential process data. And you can see actually when we use this kind of thing, put into ChatGPT, and we can get something, but it's still in the exploration stage. It's not that concrete yet. Based on these four methodology, when we handle this kind of sequential data, so we can go inside to see each one what kind of results we can get. So the first one, let's come into the mini sequence. We also call them as n-grams. So the mini sequence is just very similar like when we have the text mining. So we can say, I'm happy to give a talk today. And for this sentence, and chunk them into small pieces. So you can see we can have a unigram so that each word will become a gram over here. So I am happy to each one. Actually, we separate them into the unigram. And we assume each word will be independent to each other. And when we have the bigrams, so that means we combine two adjacent words together into one gram. So we can say I'm happy to give a talk today. So like that way. And also sometimes you need to consider about the punctuations. And for that one, actually, we assume between the bigrams, they don't have any dependency to each other, so that's independent. But within the bigrams, and we will consider this kind of a joint probability then. And then the trigrams, we will have every three words adjacent to each other combined as a gram. So for example, like I'm happy to give, like that way, give a talk. So you can see actually this kind of a text sequence is very similar like a click string. And we will have this kind of action sequences. For example, we can say a typical one is like students come inside of your interactive task. They can have start and then click into the spreadsheet. So to find some information in the spreadsheet and type into a kind of first name or full name there and to find whether they can find this information. And then switch back to the email page, and then email page they can type inside and then send email out. And then students can click on next and next OK. So that is, it confirmed to say they want to go to the next question. So very typical sequence for the students solve one interactive item. So you can see in this one, if we chunk them into small pieces, we can have 8 unigrams, we can have 7 bigrams and 6 trigrams. So it's a kind of a count. It's similar like text mining. You can count the raw frequency from each gram. And then we can get this kind of gram and to make some analysis, because now the gram becomes a kind of variables there. But when we count them, actually, we want to give a kind of weighted frequency. It's similar like when we have the text mining, we will use TF-IDF. So it's a kind of a adjusted way to give the weights to each word. But we're similar here as in the sequence. For example, in the sequence, we will say we have the sequence A and the A1 until AI. It's a kind of each action within the whole sequence there. So in this one, we will have 2 parts of the weight. So the first part, let's come into the inverse sequence frequency. So inverse sequence frequency actually consider about not only yourself, the actions, but also consider about all your peers, their sequence. So in that way, it's similar like when we have stopping words in NLP. And if you count for everyone have the same action, so that means this action will have a very small weights over there to contribute. For example, when the N equals to SFI, so SFI is a frequency of sequence that contains action I. So that means if everybody is the same, everybody use the same action here, so this action will become 0. So that means that this action will not contribute information in. And the second part, when we have the weighted frequency, we will use a damped term frequency. Damped term frequency, actually, that is to say, within your sequence and how many times one action will occur. to say if one student click on one button for 3 times, that should be different from 3 different students click on that button, each person 1 time. So actually that one give you kind of an adjustment on that, because for students click on that button for 3 times, so that means that this button is very special or very particular for this student, right? So this kind of will be higher for this specific student. So based on that, we will have this kind of term weight, not only for the raw frequency, actually we adjust them into the weighted frequency. And based on the weighted frequency, we can put it into a kind of feature selection model. So in the feature selection model, we can either use a chi-square feature selection model or likelihood ratio, this kind of selection model. There are quite a lot of different ways you can use. But here we use a very straightforward named chi-square feature selection model in the machine learning. And also in this model, we put into the large scale assessment, you can see for this cube, actually we can have a different layers. So we assume each country will become 1 layer. So that means we have the Japan, we have the Netherlands, we have the United States, and also the other countries. And for each layer, actually you can see we can count the actions, and also not actions in the correct group, action in the incorrect group, and also not this action but still in the incorrect group. So you can see we can calculate the A, B, C, D within each country. But if we want to aggregate them together to say we only want to check for the correct and incorrect, so we can do sum up all these A's in the correct group and sum up all the things in the incorrect group. So that becomes a kind of binary. But if we want to see, to say United States against the other countries, we also can do that, right? We just change this cube into another angle and to say, okay, we just want to calculate the Japan against all the other countries. So the aggregate level becomes into country then. So you can see, and based on the chi-square feature selection, we can have just to say we calculate distance between the variables independent. We assume they are dependent and observe the count is close to the expected count to see how much actually they differ from each other. And weighted actions with the higher chi-square are more discriminative in classification. So that means that is the most robust one. We can see actually between either correct or incorrect group or a country against the other countries. And then we can rank in the chi-square score of each action in a descending order, and action ranked to the top was defined as the most robust classifiers. So for this one, actually, it is kind of easy, straightforward way. Actually, you can get this kind of a value down for the chi-square. So for example, if we put into the PIAC like this kind of a study, so for the correct group and the incorrect group, we can easily to find when we use the unigram and bigram and trigrams. To say in the correct group, we can see the people actually easily to using the tools such as a searching engine and sorting with a clear subgoal. So you can see, for example, student will use a type in, so that is using searching box, and also using sorting in a big spreadsheet so they can find key information out. And also it's interesting to find in the incorrect group, we can have the hesitative behavior because the students will using cancel a lot. So you can see they will click on next, but they will not directly go to the next question and they will come back. So a next and next C or next C next. So you see, actually that is kind of a new things we captured actually into the incorrect group to see what kind of things they are working on there. And also for the incorrect group, we find they are using the help function a lot and aimlessly save their results in the server. And of course, we also can see the non-response pattern from the start and next to final ending. So that means that there's no actions in between, but just a click to the final one. So this one actually could be used not only in the incorrect group, but actually can put into the non-response or the missing response part, especially based on their different time threshold over there. And also we can calculate to say by the country level and aggregate level to see whether United States, Netherlands, and Japan in this study, they were consistent in the correct group and the incorrect groups. In the correct groups, actually, we can find they are quite consistent to each other, and it's pretty high in the mean level. Is 0.79, is closer to 0.8. But in the incorrect group, actually, we find they're only 0.71. So that means actually, if the students generally solve one question if they are make the correct, so generally they will use a similar way to make it correct. But when students have the incorrect answer, they can have different ways. They can have a multiple diversified ways to make it incorrect. And also at the same time, we also can calculate for the features by each country. So for example, just now I said, if you change the cube into another direction, you can calculate to say one country against the others. And we can find the United States actually is a kind of a double click on the email page. And also for Netherlands, actually we find more likely use a full name and given names when they're doing the searching in a spreadsheet. And when we come into the PIAC for this question, and Japanese group actually showing a kind of a different way. So Japanese actually is a surprisingly to find the spelling mistake is the most robust one in this country. And actually, we need to check back to see what is happening to this country, right? And when we check it, we find because Japanese is a character-based language, it's different from alphabetical language. For example, like English or French, so that they are alphabetical language. In alphabetical language, we basically will have the space in between to say I am happy today. So I am. So you have to have this kind of space in between. So that is a kind of a compulsory. But character-based language, we generally do not have this space in between. So that is actually design error in the PIAC when we did this kind of item design. So we say this kind of compulsory space should be here, and between the first name and last name. And so students are confused over there because in Japanese they do not have this kind of space generally. And so you can see students actually very persistent and to say click. They will search again to find spelling mistake, and finally they have to give up or to find other ways. But the Japanese group actually is very persistent in their behavior. So you can see not only to have their spelling mistake showing up, but also we find Japanese group, they also have this kind of strategy change. So after this strategy change, so for example, they have spelling mistake and they change the sorting into the sorting way to find the key information. So that is a good sign actually for this group. So PIAC actually, when we find Japanese, they still ranking pretty high, but from their performance pretty high. But actually, when you check for this group, their spending time and also the length of actions, they are much longer than the other country, very significantly higher than the other country. So this is kind of a question over here. So you can see that is also the reason why we say the process data matter. If we can find these things in the field trial, actually we can avoid this kind of thing, prevent this kind of happen. But actually that is a very early time when we use the process data. So in the field trial, we didn't have a chance to look at the process data. We directly come into the main test. So that is kind of a pity. In the main test, we find this kind of problem showing up. And also we can see when we use the n-grams, we also can use them actually to make the prediction. So how much actually the n-grams from process data can support our assessment, it looks like here. To say we show up this kind of use a different number of a number of items and the correlation about their final score. And also you see this one actually we will show up to say the black one is answer only, and the red one is with the process data. So you can see if we put them into adaptive testing design, and based on the items over there we can put inside. So you can see if the standard error comes down, right? And if we will only use the answers, so we need to use the 7 questions. But if we use a process that together in, so you can see actually we use only 5 items will be good enough as the 7 items to have their standard error estimate. So that means we can save 2 items at least when we use the process data. So that will largely actually help the item developers, especially when we design this kind of interactive items that is very, very expensive. So if we can have this kind of process in, that will be more cost effective, actually can be used in the test development. And also we can see quite a lot of new application of the mini sequences that use n-grams. For example, we can use them for test development, quickly check the robust actions by correct and incorrect group, or identify the key actions used by groups with different background. And also teacher can use them for the dynamically compute the occurrence of the action with a joint likelihood, and also adding the time pause as an action into the n-gram to identify when and where this kind of pause occurs and associate the before and after which action. So that part actually is from the n-gram part. So you can see n-gram is very straightforward. The advantage, actually, you can directly use them as a kind of variables. But in disadvantage is to say you have to trunk the whole sequence into small pieces, and that will influence the dependency between the actions. And we put our codes over there for the synthetic data set and our demo codes in the materials. So please feel free to play by yourself when you have time. So after we talk about this kind of gram-based, so gram-based actually from the sequence come into the gram actually becomes a variable. So that is a straightforward way, and we can directly use this kind of gram-based features and together with the response data. And the second approach actually we want to introduce is for the sequence proximity measures. So sequence proximity measures, actually we will not trunk the sequence into small pieces, but actually we will calculate the sequence distance as a whole sequence there. And for that one, actually, we can do the sequence similarity measures, predefined sequence, or the pairwise ones. And then we can also do, to say, sequence similarity with the incorporation of the timing information in, and also distance measures and latent feature extraction from this way. There are many ways actually can calculate the distance between the sequences using the distance matrix. And here actually today we want to highlight two very important similarity measures over there. So the first one I'll call them as the longest common subsequence, LCS. So longest common subsequence actually is straightforward, like to see we have two sequences X and Y, and in between the X and Y, actually we want to find which one actually is the longest common one from these two sequences. So assume we have the BDCABA from Y, and also we have ABCBDAB from the X. And so that is actually, we calculate this matrix by each cell, and to say how we can catch these cells. So say you use the A compare with B, and A compare with BD, A compare with BDC, and A compare with BDCA. And then we will find, okay, A is over here. So we change the 0 to 1. And then we'll continue to do all the cells. And finally, you will find the shortest path starting from this corner back to the beginning. So in this way, actually, we can easily to find, to say, each action and the other action, what's its common sequence in between. And we use that one actually for, to say, we have observed the sequence from students, and also the test developers develop their own path or their own sequence. And then we can calculate the students, their path, and how far away from the predefined one, from the test developer design one. But there is a kind of way actually we need to consider about, to say, each item possibly not only have one solution, but possibly will have multiple solutions here, right? So for each solution, we will need to calculate their longest common subsequence. Here's a kind of example to say we have the example, like to say the item developer gave us 4 sequences, to say that is a predefined sequence, and they're equally weight, to say students either choose either one will be okay to solve the question. And then we have observed the sequence from the student, and we will use this observed sequence need to calculate longest common subsequence from each defined predefined one. So predefined RS1, RS2, 3, and 4. And then we can calculate, to say, their longest common subsequence compared to each predefined ones. We got their find the longest common subsequence and to count the length of them. For example, this one, the students actually use the longest one when he or she actually choose the number 4 strategy over here. So that means that this one actually will showing up to say the most likely the students will choose this solution to answer the question. But here actually we need to admit that to say we say that is only the most likely, because sometimes we'll have this kind of overlap or double or multiple membership of the students. For example, when the students they choose one solution to solve the question and use the other one to double check, so that makes sense, right? And so for that one, actually, we didn't take that one into the consideration right now in this study, but actually that could be interesting one to make this kind of multiple membership for the students and to calculate the probability for each one. And so you can see actually for this one, if you calculate the observed sequence against a predefined one for each question, and then we can create some new variables here. For example, we can create a similarity and efficiency. Similarity, that means we want to calculate to say the length of longest common subsequence with the ratio 2 against the predefined sequence to say how much actually your solution actually compare with the predefined or how much similar they are. So that is similarity. And the other one we call them as efficiency. So we use the longest common subsequence divided by the length of the observed sequence. So in this way, actually, we want to find this kind of effective longest common subsequence actually could take how much in your observed sequence. And in the other way around, to say we want to capture to say how redundant the students use these kind of redundant actions. That means they actually not necessary to take some action, but they still use them in their solutions. And basically, actually, we want to find students, the best students should be the very concise solutions, and also they do not use redundant actions, and directly can go into the correct ones. But in the real practice, actually, it does not show you like that way. So you can see that this one is coming from the association between similarity and efficiency with the latent trait. And that is from the PX study. And we find actually from similarity, actually similarity will go up. So you can see from 0.2 to 1.0. So that means actually they can, with their latent ability going up, their similarity actually will also going up. So these different cells actually represent for different level of their performance. And also we can find within the extreme level, for example, below level 1 and level 3, actually the white bandits over here actually is small. So that means that these two groups are actually relatively stable. So that means if the students in the below level 1, so that means almost every item, they will not follow the predefined sequence. And also level 3, so that means almost every item the students will follow the predefined sequence. And you can see the variance actually in between is bigger in level 1 and level 2. In this kind of sense, it's showing up to say students are more based on the items. Some items they can follow that, but some items they are quite far away from the predefined sequence. And when it comes to the efficiency, actually we find efficiency actually is a different story. So for the really great students, because they are come into level 3, for these group students, actually they will use a longer sequence, and their efficiency actually pretty low. To say these group students actually will use long sequence, many actions to do more exploration to ensure they can make it correct when they solve this item. So you can see actually their efficiency is smaller, is lower compared with the students actually come into to the low performance groups. So you can see in the longest common subsequence, actually we can find what is the longest common subsequence between observed and also the predefined. So or the pairwise comparison. And another a kind of way we want to calculate from the sequence distance, we can call them as a dynamic time warping sequence. Dynamic timing warping sequence is relatively different from the longest common subsequence and also the other sequence. So for example, the the traditional one, actually we want to find this kind of distance, for example, from Euclidean or Manhattan. So which aligns each data point from the action, from the sequence, corresponding to only one data point in the other one. And also they are having this kind of ordered sequence. But in the DTW1, actually that will be different. DTW1, actually they will allow us to have one data point to align to multiple data points to the other sequence. For that kind of way, actually they will help us to find the most warping way, actually to find the most optimal path to find this kind of two sequences. So in this way, actually, we need to calculate not only direct to say the data point in one action sequence compared to the others, but also need to compare also their neighbors in the data point. So for example, when we have the A sequence as 1, 2, 3, 4, 5, and the other one, the B, we have 1, 2, 3, 4, 3, 2, 5. In this one, actually, we will calculate them into this kind of matrix to calculate the distance. So for example, if we want to say, we want to find the 6 between this A5 and also B2. So in that one, actually, we can use A5, so that's 5 minus 2 is 3. And also within their neighbors, and we want to find the smallest one within them. So 10, 6, and 3, so we find smallest one as 3. So we use 3 plus 3 equals to 6. So based on this kind of rules, we can also get the calculation for the added distance in this matrix. And then we need to find the shortest path from the corner and back to the end. For this method, actually, we need to recode the categorical variables into the numerical variables. For example, we need to redefine, like to say, the students come into different page. And so reading page or something like that, and then we need to recode them into the numerical value over there, 1, 2, 3, 4, 5, like that. So this method actually used quite a lot for, like to say, the stock market and all the other things. So explain like this. For example, when we have the first one, the sequences actually look similar, but actually they happen into different time window. That will be exactly similar as when we have when we have the students, their actions, and also solve the questions. Because sometimes students will solve the problem quicker and also use they're at the beginning of the time actually to solve them. But some students will think a long time, have the pause a long time, and then they start to solve it. So that means even the students, they have a different time pause, but they still use the similar actions. If we use the traditional way to calculate the action sequence distance in between, so they will become not similar at all, just like the first one. So this one actually, if you calculate the similarity between them, actually becomes 0. So they think they are not similar to each other, but actually they are. But that just to say they are happening into different time window over here. If we shift the blue one to the right a little bit, so you can see actually they are overlapped to each other. So it's similar in the DTW methods. We want to find, even though they happen into different time window, but they still have the similar shape. So similar thing actually in the stock market, you can see the two stocks actually for one, the yellow one and the brown one. If we shift the yellow one to the right side a little bit, so you can see actually these two stocks will become overlapped to each other. And we can use this DTW method easily come into visit and revisit navigation, use the sequence distance. So, and then based on our distance calculation, distance matrix calculation, we can class them into different patterns. We can extract the patterns out. So for example, the first one, we call them as normal pattern. So students generally will just navigate to say the first action, the first item, and to the item 16. And the second one, actually, we can see that is multiple back and forth in revisit patterns. So students actually do, they try some items and then they come back and then they try again. And the third one, actually, we call them as a double review patterns. We also see students actually do old items to the end, and then they will come back to make the double check. And the last one is quickly skip patterns. So you see, using DTW method actually is a helping us to find, even though they are tapping into the different time window, but actually they have the similar shape. And based on their shape, based on these kind of patterns, we can put them into the clusters. And also we can use them into the time sequence. So for example, the first one, the students actually use a little higher time in the first question compared with the general one. And the blue is the general one, the red one is the individual student. So you can see after the third question, actually students follow very good into the similar pattern as all the other students. But the second one, actually, you can see the students actually obviously to use a longer time in the first couple of questions to get used to this kind of environment. And then they can follow a similar pattern as the other students. So for this one, actually, we also can calculate their similarity to each other. And to say this student possibly we want to show it to the teachers, and teacher can give more intervention or guidance at the very beginning of the test for these students, or at least the teacher can understand better to say which items the students will meet this kind of challenging, and also can give them helpful and immediate help to help them. And we use the DTW method also into the ICLS 2018 from the IEA test. So it's a kind of a case study when we use the DTW method. So this one actually, ICLS is an international computer and information literacy study. So in this one, we have the literacy and also computer thinking 2 parts. So when we do that, actually, that is generally used a student in 8th grader and also from 9 countries and the regions. So you can see actually the items look like this. It's very interactive for the students. They need to control the farm drawer here. The farm drawer, actually, they will drop water, drop seed or fertilizer inside. And here is a kind of a code, programming code module. So students can drag them into the simulation environment. Or if they think that is not correct, they will drag back. So for this one, actually, we got this kind of programming code questions and also debugging questions and also consolidation. And it's very interesting, actually, when we have this kind of data and to see them. So you can see we have almost 20,000 students in this test, but over two-thirds of the students, they will have this kind of missing. So that means 2/3 of the total sample in this task, actually, they will show at least one missing response there. And so we want to understand where the students actually got missing and why they have this kind of missing response over here. Of course, when we have this kind of, this task, actually, we have 9 tasks inside for this module. And when we find actually it's approaching to the end, it is missing, so that makes better sense, right? But actually, we also want to check for whether other questions, they still also have this kind of problems. We use the DTW methods and to put them into recode the score as 1, 2, 3, 4, and 0, and 9. So you can see 9 actually represent the missing, and we want to understand where's the 9 locates from this kind of pattern. So, and then we use the sequence clustering to find this kind of things and make the pairwise sequence distance matrix. So it's interesting, actually, we finally got this kind of sequence clustering result and to find the non-response pattern. So it's very interesting, actually, to find the cluster 3. So cluster 3 students, they showing up to say they miss the first 2 items, not the final one, because the final one, see cluster 5 and 6, we understand to say students possibly do not have time, but they miss the 2 first questions. It is because these group students actually, they did not read the instructions very carefully. And they just think the first 2 questions is a kind of warm up and does not count into the final score. So they just miss that. So you see, actually, also the first cluster showing up the student do not have quite a high engagement inside, because at first they still make some actions over here, and then you can see starting from item 3, actually they just become 9. They're just missing all the things. And also for cluster 4, interesting to find students stuck into the item 5, and then they will just miss up all the questions after that, because item 5 actually, when we check back to see the items, we find item 5 actually before 1 to 4, actually the student only control 1 bar for the farm draw. And when we come to the item 5, the students start to have control 2 bars. So the 2 bars actually will be more challenging than the first one. So students, if they put a lot of time at the very beginning of the task, actually they do not have enough time come into the number 5, or they just think that it's too complicated, they just skip them. And then we also find question item 7, actually it is starting from 2 bars come into the 4 bars. So still need to control the 4 bars. That is even more complicated. So you can see students start to get missing over here for that kind of a perspective. And so basically that is starting from +6. So you see actually students spend a lot of time in item 7. So item 7, they even got the highest score over there as a 4, but finally they do not have enough time to finish all the questions. And if we put them response time inside and to find the time allocation and make them into the cluster, so we can find actually the corresponding to the navigation path, actually we also get this kind of time allocation path. So you see actually students spending quite a lot of time in item 7 look like this, and then they quickly drop back. And also students generally spend more time in item 5 and possibly do not have enough time to finish all the questions. So that is basically, which introduced to say we have the longest common subsequence and also dynamic time warping methods for these two. But we also find this either approach is perfect, that is true. And sometimes you need to combine their strengths, because sometimes we just directly use these two methods, each one will be good, but sometimes we need to combine them. So when we combine them, actually we find the longest common subsequence actually allows a sequence having different lengths and have intermittent non-matches, that is good. But LCS do not have the time information inside. And because that is basic on the actions, or if we can add into some pause inside as another action inside. But DTW methods match a non-linearly stretch or compress a sequence and finds the optimal path through a matrix of option of points represent the possible time alignments between the sequences. So that is pretty good because they give you flexibility to calculate the distance. But the time aligns from the beginning to the end, which may impact the similarity measure when the action sequence lengths are significantly different. So that means if sometime we can find the some student is not engaged at all, they only have 3 actions, but for the other student probably they will use 500 steps to finish one question. So you can see the length will be significantly different, but we still need to have this kind of a DTW to align them to each other. So if the length is totally different from these two sequences, actually when we calculate the similarity, it may not be that accurate enough. So we will say sometimes we want to combine the strengths together. And that is actually a kind of interesting way. So I think that for a while, and then I got some inspiration from the music retrieval. So from the music retrieval, actually, it is really located there because that is a get from my son when he plays cello. So actually, that kind of music, we have 2 dimensions, very important. So one is intonation. So that means you need to be accurate to come into that tune. And the second one actually is for the rhythm. So rhythm, actually you need to calculate and to say sometimes it's a half, sometimes it's a quarter, right? So you need to actually also accurate to that one. So they have 2 dimensions, exactly similar like when we have the process data. So in the music, we have 1, 2, 3, 4, 5, 6, 7. So we have 7 notes. So that will be similar as our actions. You need to want to in tune for the process actions. But at the same time, you also can consider about the rhythm in between, right? For example, in the music, we will allow them to have extension like a do, re, mi, right? We have this kind of extension. But that will be also can be coded as do, 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 re, 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 mi, 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 like this one. So if we can also make the process data like that one, so that will be easier for us to combine the LCS and also DTW. Because, for example, in the music retrieval, they have this kind of questions like to say 4, 4, 5, 5, 6, 6, 7 versus 4, 5, 6, 7. So we can get longest common subsequence of 4. And the second one, 4, 2, 5, 3, 6, 1, 7, 2 versus 4, 5, 6, 7. They also got the longest common sequence as 4. But actually, they also want to get this kind of a rhythm inside and to see whether we can make a better distinguish between them. So we find actually we could use this kind of time warped longest common subsequence. So we call them as TWLCS to combine them together. So in the process that actually we will do like this. So we will have the A, B, C, this kind of actions. And we know A and B between them, actually we have 20 seconds. B and C, we have the in between have 40 seconds. If we will take 10 seconds as a kind of unit, it can be put into like AA, repeat them. And then we have the B, 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 and then finally we have C. So that means we will use this new coding scheme for the sequence and to make the comparison. So in that kind of way, we can give a kind of example like to say 41516171 versus 4567, and longest common subsequence is 4, DTW is 18, and TWLCS is 4. And 4455667 versus 4567. So we can see longest common subsequent becomes 4. DTW is 0. And 0 actually that means that they're exactly similar to say 4455667 and extension 4567 that they are the same in the DTW. But in the TWLCS it becomes the 8. And 44556111177 versus 4567. In the longest common subsequence is 4, DTW becomes 24. So 24, that means that they are not similar at all each other. And TWLCS equals to 8. So in this way, actually, we can find from the LCS, it is not sensitive when we change them in between, because it doesn't matter what kind of things is not matched there. They only care about the matched part. But the DTW method actually is good to see this kind of similarity between, especially for their shape. But also we can find if we come to say very extreme line, the length of them actually that will be giving some error term into the similarity calculation. And TWLCS actually looks like to say that is what we want to find the students actually over here. But we also see actually the students come into TWLCS like 4455667, and the following one, when we add into the new actions inside, actually the TWLCS is not that sensitive over there. And we would recommend to say actually in the following study, we could actually to use a DTW method and to make the first clustering, and then within the clustering we can continue use the TWLCS and to find what's the difference between them. You see actually for example there because the DTW method actually is very sensitive for this kind of a shape, and they want to have the shape also as a similar things over here. So we can see the step for sequence similarity measure and clustering. So basically we can use the pre-processing two-dimensional sequential data, action and sequence, and converting them into the one-dimensional sequential data by repeating the actions by time units. Because if you have two separate sequences, actually that will be hard to make the calculation. If we put them into the one sequence, that will be easier. And step 2 is compute the pairwise sequence distance matrix based on the product from step 1. And then we can use a different clustering methodology there. For example, we can use a partial clustering on the distance matrix from step 2 and to group member sequences to the same group with a high similarity. And the last one is to decide the optimal number of clusters by a variety of indexes. For example, we can use silhouette index, down index, etc. And here is a kind of a case study when we use academic resilience for students. So academic resilience students, actually that is for students who are coming from the low socioeconomic status, this kind of family, but they actually perform pretty well in academic. So you can see actually for this kind of group students, actually they will show this kind of persistency. And we want to check this group students, their behavior when they solve the questions in the last skill assessment to see whether we can capture some behavior patterns showing up. So we put them into the team's 2019 data, and especially for 2 scientific inquiry tasks. We have sunken ship and we have pepper plant. And for this study, actually, we use the Norway data and focus on 599 students, and we put them into SES and performance as two dimensions, and then to have the students in the high performance, high SES, low performance, low SES, and the other way around. So we want to actually focus on the high performance students, but with low SES. So that is students coming from the relatively low SES family, but they still have very good performance. And for their sequence, actually, we will do like this to say we have timestamp, and we calculate the interval in between and use the 10 seconds as a repeat. And for example, students, they have the navigation sequence over here. And then based on their navigation and also the time in between, actually, we can repeat them like this one. So after repeat, we can have this kind of sequence. And we put each like this kind of sequence into the analysis and to see what kind of clustering we can get. And it's interesting, actually, we use these 3 methods. We use the longest common subsequence, the DTW, and TWLCS. These are 3 methods to visualize what constants we can get. And for the LCS, actually, because these methods do not care about time, but only care about the action sequence. So you can see, actually, if we put them into a clustering like this, so we can see actually the yellow one actually located over here. This is a bunch of them, but actually only very small number of students will come into the other cluster. DTW method is a little bit better because they can help us to find all these kind of students located in different ways. But actually it's a kind of mixture between different memberships. When we use the TWLCS, you can see actually it's showing up in a very good shape. And of course, it is not linear to show like that way. So students actually located in the green, in the black, and also for the yellow one. So they are separated very clearly. So that means actually from that way, we can understand the clustering actually will be very clear clustering. So they do not have quite a lot of overlap from each other. So basically, when we check to see why this kind of DTW method doesn't work well, compared with TWLCS. So that is a major reason is because the students, their navigation sequence will be totally different. Because we do have students, they go back and forth many times, like to say over 300. And some students, they only go for that kind of 13 items to say only 13 steps. And compare with the students to have 300 steps. Actually, that's a significantly different of the length. And so that will give us some confusion, some challenging when we calculate the DTW and to see their clustering results. And so this one is when we're mapping back to the resilient students, so we can see when we use only the DTW methods, actually it only can find here for this shorter sequence, actually it could not give us too much information about how to interpret the students. But when we use the TWLCS, we can get very clear 4 clusters. And for the red one, actually, that is for students from the resilience group. So that is, they will do quite a lot of time to have this kind of double review pattern to say they come from the first question to the end, and then they will come back. But also we find some problems of the resilient student, because this group of resilient students, so they come too persistent. For example, they will spend much time on one question and they will not continue. You see, this is kind of flat line. So that means students do not actually continue on. So they're just stuck there, and they really want to find a solution for one question. And actually they forget to say, they do not wisely to use their time to finish all the questions. Another new trial actually now is we try to use advancing sequence clustering with the image processing. So the image processing, actually, that will be for each student. After they finish one task, they will become an image. And so we have the time and also the action sequence. So locate into this kind of image, and then based on the image, so we can make the comparison. So this way actually will be more generalized way to calculate for the students their clustering or the other things. We put the demo codes into the materials, so you can find them using the synthetic data set and use the pre-processing and LCS and also DTW methods there. I will quickly go through the latent sequence modeling, and also the latent sequence modeling actually is for when we have observed the sequence and we want to have the latent state behind them. The latent state under them actually will be to say we want to calculate what kind of latent state and what's the transition there. So we can see actually for Y1, Y2, Y4 until YT, so that is observed actions. And under them, we want to find the latent state. For example, some items, some actions that will represent for each state. And within between each state, actually we will have this kind of transition, like this A parameter. We can have the transition probability matrix. And B parameter, actually that is the action actually represents the S, represent this kind of a latent state. And so we have the initial probability matrix, and also pi is the initial value for that. And based on this hidden marker model, when we have this kind of latent state, we can better interpret the participants when they do when they really do some actions over here. So for example, when we check for the LDOS in the PIAC, so we have the high literacy and correct group. So they have special different states, like to say using the sorting to handle the question. So that means actually in the other state, sorting is not significant showing up there. And also we can see it's interesting to find to say, because for the incorrect group, at the beginning we say for the incorrect group, actually they will showing up this kind of hesitant behavior. So that means they will go back to see to check or to see what kind of things they can do. But actually for the incorrect group, even though they click on the cancel and go back for this hesitant behavior, but when they go back, actually that is very diversified to say they go back to say they do not have quite a clear aim or goal to go back to check some place. But for the correct, for the incorrect high literacy, that is high level people, when they go back, actually they will very clear to see which part they want to check to see whether they make a correct solution there. So that is the difference when we give this kind of a latent variable, when we give the covariant variable, for example, like a low literacy and high literacy part. So this one actually is also showing when we including the time inside, so that it elapsed time state in the hidden marker model with covariates. And the first one is the cluster 1, so we can see the person actually coming into this state is very clear state transition. But the second one is for the low level people, when they come into this one, so you can see from the latent state, we can find they actually back and forth quite a lot of times. And also their pulse state also is much longer and much clearer actually compared with the cluster 1 group. Okay, the last part actually is something new using large language model. And this one actually becomes more complicated when we consider about more dimension of the sequence. I call them as a process information bubbles. So basically when we have the process data, we'll have event 1, event 2 until event t. So quite a lot of events over there. And then we will have the time in between to say what kind of time in between. This is the second layer of the sequence. And also some questionnaire and also large scale assessment now also have this kind of confidence to say, after you solve the question, they will ask you how much confidence you are in this question or how much effort you put in there. And so that is also a kind of sequence. And also students will have the anxiety, and also with their time lost, actually they will become more and more anxiety higher level. And so that is also kind of sequence. if we're adding to the eye tracking movement within the time, so you can see actually that is kind of quite complicated multiple sequence data structure inside for the process data. And then the text mining actually will be the special case here, because text mining will only consider about the word and word dependency in between. So there's actually not a kind of time in between the word. So sequence mining considers a multiple dimensional sequence, and but also a text mining treats a unidimensional sequence. But we can use the unidimensional sequence as the first step to train this kind of large language model and to see whether that can work in that one. So this one is a kind of showcase for when we want to use process data from the sequence and actually to predict the missing response inside. And so this one actually showing up the missing value with the process data. And we care about more about this kind of BERT model and use different alphabetical order, random order, and real order in the assessment. And also because missing data is a kind of a small sample there, and we also treat them into naive undersampling, naive oversampling, and data-specific argument. And this one shows up to say we will have the response. If we don't care about the process data, we'll only use the response only. So you can see when we calculate this kind of a missing prediction rate, so U02 becomes a 0, so it's a very small value. But if we compare using the process data inside, so we can see actually we got some information there, even though the precision and F1 scores is not that great, but we learn something actually compare with only the response data there. So that is kind of a new trial into using the BERT model, and also we try to use a CoxNet model as well to make the prediction. So that will be later. If we got some concrete results, we can make a share. Okay, finally, let's come into the discussion on the outlook. So we can see there's some new trends and challenges on process data research, especially we want to integrate the process information into the ability estimates, and also integrate a multi-source of data, for example, qualitative and quantitative with the process data, with eye tracking, mouse trajectories, anxiety and VR, and also think aloud methods into the process data. And also some thoughts for the future study. So process data is a kind of personalized behavior data, may add more weight in the assessment model in the future to compensate the risk of AI manipulation. And also one-time assessment is not the target of education, but tracking the students' progress and providing timely and helpful supports. And the process data could be given a broader scope of dynamic and longitudinal study. So sequence methods could also be used in the educational policy tracking to see how this kind of policy can be showing into the large-scale assessment or what's kind of effect over here. And also we think the post-assessment process data analysis could be progressed to dynamic process data analysis throughout assessment and bring new meaning for the adaptive testing, not only from the responses, but also from the interactions. Okay, I'll stop here. So acknowledgement for the grant, so with support for the for this study actually. And here are some references list for this talk. So I will put all of them into the materials. Yeah, thank you very much. If you have any questions, please feel free to put into the chat. And we will have the short break, I think. So Zhong, you'll put it into the break, right? Or is there any questions so far? Because I cannot see actually.
Currently, there's no questions.
Okay.
Yeah. So
I think now it's 6:30. As our schedule, so we will come back at 6:40. Would that be good? Susu, would that be good?
Yes, that would be good. Thank you.
So we will come back at 6:40 and we'll continue for Susu's section. So that is focused on the feature-based process data analysis in the large-scale assessment. Thank you all.
Hey, Zhongyu, can I start?
Yes, yes, of course.
Okay, thank you. And you can see my slides and everything, okay? All right. Okay, thank you very much. Welcome back to the second part. And in this part, I'm going to talk about how we can use features extracted from process data in some subsequent analysis and large-scale assessments. I'm going to present two case studies, and both of them are going to be involving the NAEP data, which stands for the National Assessment of Educational Progress. So here's a brief agenda of the second part. I'm going to first start with an overview about our empirical problem related to the use of NAEP process data to understand the achievement gap between students with disabilities and their peers. And then I'm going to go on to talk about the two case studies. The first case study is going to use features that are what we call expert-derived from process data. The essential idea is that you have some idea about what kind of patterns might be useful and cognitively meaningful, and you try to find them from the action sequences, define variables based on those. And we're going to try to use those features to understand the effect of extended time accommodation for students with learning disabilities. And in the second case study, I'm going to discuss how we can work with data-driven features. So these are methods where we extract some features that we know captures the original sequence information, but we essentially have no idea about what exactly are those features capturing. So what do they actually empirically mean? But we can still use them for some exploratory analysis. And in case study 2, I'm going to discuss how we can use those data-driven features extracted using multidimensional scaling to explain the performance gap via latent class mediation analysis. But first, I want to talk a little bit about the empirical problem motivating these case studies. So the NAEP stands for the National Assessment of Educational Progress. It is a continuous large-scale assessment in the United States that tries to monitor how US students and regions are doing over time. It usually is administered every 2 years. There are a few key subjects like reading and mathematics that are administered to students at the 4th grade, 8th grade, and 12th grade. So NAEP is essentially a survey of how US students are doing. And of course, we want to capture the students from specific demographic groups and with specific needs as well, including the students with disabilities. A student with disability is assumed to be able to participate in the NAEP if they can participate with accommodations that are allowed by NAEP. And schools are actually encouraged to have students with disabilities participate whenever it's possible. So NAEP defines a student to have disability to be a student who has an individualized education plan or IEP for reasons other than being gifted or talented. It can also include students with a Section 504 plan and any other students who have received an accommodation under NAEP, excluding English language learners, which are essentially students whose native English language wasn't English. To give an idea about what are the types of disabilities, here is a plot I pulled from the NAEP website, which describes the percentage distribution of students from age 3 to 21 who are served under the IEP. You can take a look over here that we can see that the largest group of students with disability was actually with specific learning disability. And this is followed by things like speech or language impairments, other health impairments, autism, developmental delay, etc. For both of the case studies here, we're going to look at some questions that are related to students with specific learning disabilities. So this largest category over here. If we take a look at their performance on the NAEP assessment over time, it's actually shown that over the years, there is a long-standing math achievement gap on the NAEP assessment between students with disabilities and their typically developing peers. And we should note that this is despite that, first of all, the IEP provides specialized instruction and support to help those students progress through the curriculum. So the students receive a lot of support already in their education. And second, the assessments like the NAEP have been engineered with all sorts of universal design tools and accommodations to try to make the assessment more accessible for these students with special needs. But despite that, so despite the efforts on the education part and the assessment equity part, we still see that across the years that we display over here from 2013 to 2017, there is a substantially larger proportion of students with disabilities who are at the below basic level on the NAEP math assessment. And if you look at more recent data in 2019 and 2022, you can see that this trend persists, where if you look at the students who are not identified with disabilities, about 34% of them are at the below basic level, but 78% of them with disabilities are at the below basic level. So then our question is, what can we do about that? So starting in 2017, the NAEP math assessment transitioned from a paper and pencil-based assessment into the digital assessment known as the eNAEP. And it is administered to students with a Surface tablet and a stylus. Here's a screenshot of one question from the eNAEP assessment. So this is like 1 out of 15 questions. So this is item 8 from a 15-item block in one block of NAEP math questions for the 8th grade students. You can see that the question itself looks pretty much like the kind of like math multiple choice questions we see in the paper pencil test, with a couple of small differences. The first is you can see that the student can actually like eliminate different options. They can clear answer to remove their answer over here. They can also use various tools that are, you can see them on the top of the screen on the top left corner over here. So for example, they can use this zooming to make the font larger. They can use this T ... thing, which means text to speech, and that can actually allow them to highlight some text and try to read it out to them instead of having them to read them themselves verbally. And this little thing over here is actually a scratch pad, which allows the student to write on the screen over here in case they want to draw some lines or like write down some equations or computations procedures. And you can see that on the right over here, the student can also move between items, right? So for example, they're at page 8 right now. If they click 15, that jumps them to item 15. If they click like the back button over here, it goes back to item 7 on the last page. And the student can actually freely review their answers across pages and make answer changes. And in this process, we can actually collect test-taking process data. So here we define process data as the computer log sequence of timestamp events that documents the actions performed by the examinee in pursuit of solving the tasks. To give you an example, you can see here's a screenshot I took from a earlier released NAEP competition dataset, data mining competition dataset. And this is the raw data that they have released. So you can see that for this data set, the rows essentially correspond to the documented events. And student ID is the ID for the student. So this is student 23330000955. Accession number essentially means the item ID in the NAEP assessment context. So this is item number VH098810 is like specifically one math question. Observable is the type of the event, so like a general information about what kind of event it is. You can see that there are things like entering and exiting item, clicking next, clicking a choice, but it doesn't tell you which choice it is, which you can find actually in the more detailed coding column at the right. So here we can see that we have events like enter item, exit item, but things like choose for, which indicates that the student selected the 4th option in the multiple choice question. And of course, we also have the timestamps that corresponds to each of these system documented events. So examples of actions on the eNAPE can include things like keystrokes for constructed responses. So suppose that you have a question that's not a multiple choice, but say a fill-in-the-blank question, which we'll see later on as well. Then you can have the students typing history of what are the buttons that or the keys that they have typed on their keyboard, or like the equations that they have clicked. It can also have like their answer choices, revisions, and eliminations on the multiple choice question. Their tool usage, such as their usage of scratch work, so they can be drawing or erasing something on the screen, text-to-speech, zooming and highlighting, and also their visits and revisits, which are documented by their entering and exiting the item page. So process data can contain information that are unavailable in the final scores that can help us understand the interrelationship between disability status, math test-taking behavior, and the math performance of the students. In fact, there has been a wide literature on the utility of process data across different kinds of assessments and contexts, which show that process data is useful in understanding subgroup differences. So here are a bunch of papers you can look into. And process data is also useful in finding the differences in sequential patterns for students with correct and incorrect problem-solving outcomes, right? So Qi talked about some of the examples of these already. In our context of the NAPE math assessment for students with learning disabilities, we have seen that if we just look at the final score, well, of course, it tells us that we're in trouble, right? The scores indicate that the students with disabilities are less likely to score above basic compared to their peers, right? But our question here is, what can we do about that to improve the situation? So can we use process data to understand how this happened, to gain insights to what can we do about it? For example, we can use process data to ask questions like, are students with disabilities solving problems the same way as their peers? Other questions like when they're provided with specific kinds of accommodations, like when they're giving extra time or extended time accommodation on the test, or some sort of accessibility tools, does that actually change their behavior taking the test? And does that actually change their outcome taking the test as well? We can also look into whether students with disabilities feature specific types of wrong responses, or do they show specific strengths, surprisingly, in certain types of items. So these are some of the potential utilities of process data to help us better understand the test-taking behavior and address the achievement gap. However, the process data also presents us with methodological challenges. So the structure of process data, as Qi has talked about already, precludes the direct application of many statistical tools and models that are built for educational research. So if you think about the methods that we have learned about in our psychometric and IRT classes, or like our quantitative psychology classes, the input data are not raw action sequences, right? The raw action sequences are variable length sequences of ordered categorical events or actions. The various features extracted from process data, they might follow weird distributions. Probably they're not normal. Those distributions, we might not be able to assume that they follow very nice parametric family of distributions. And another challenge is that the process data, as well as the data-driven features extracted from process data, can contain a lot of noise. So in our context, the noise can be something like whether a student likes to single or double click a button. Does that reflect some individual differences in test-taking process? Yes. Is that important to the question we're interested in? Probably not. So maybe it's not related to why students with learning disabilities are doing worse on math, right? So process data contain information, but some of that information might be irrelevant to understanding the math test-taking behavior for learners with disabilities. In this study, we're going to, in this part of the presentation, we're going to talk about 2 case studies where we try to find approaches that can handle these challenges and to address our empirical questions. And as I've mentioned, study 1 is going to be related to using a non-parametric permutation test. We will use that to triangulate expert-derived features extracted from process data, the performance data, which is the math scores, and the survey data, and using these together to try to tell a full story of the impact of extended time accommodation for learners with disabilities. In study 2, we're going to use multidimensional scaling features and latent class mediation analysis to select the most relevant data-driven features from process data that characterize patterns of test-taking process, which can best explain the group differences we see on the final item scores. Right, so let me move on to study 1, which is the use of extended time accommodation for students with learning disabilities. This work is already published in a paper by me and my collaborator, Dr. Xin Wei, and this can be found in the Journal of Learning Disabilities. So let's talk a little bit more about accommodations. The NAEP exam, we already mentioned that students with disabilities are encouraged to take them if they're able to. The exam itself, of course, tries to be accessible to these students as well. It provides a set of universal design elements and accommodations. Here, universal design elements refer to elements that are built into the test interface and are available to all of the students. Examples of that include some of the tools we have talked about, like zooming. So everybody taking the test, no matter if you have an IEP or not, you can actually use zooming to make your font size larger. Other things include like color theming, and also like a closed captioning, text-to-speech, except for the English reading exam, which we actually care about how well the student reads. Okay. On the other hand, we have accommodations. So if the student's IEP demanded that they should receive a specific accommodation during the assessment, then NAEP provided the accommodation. So these are things that are provided to students, a subset of students whose IEP indicates that they need this accommodation. And a good example of that is the extended time accommodation. Of course, you have other things like you might have like a calculator version of the test when everybody else cannot use calculators, etc. All right. So let's talk about the psychometric implications of test accommodations. Right? So the goal of test accommodations in general, which is we try to make some adjustments to the test for a specific subgroup of students. Our goal is to increase the reliability, validity, and fairness of the scores by reducing construct-irrelevant measurement errors. And this is described in the Standard of Educational and Psychological Testing in 2014. Taking the example of extended time accommodation, or ETA, and the NAEP contest. So here can be the rationale of providing the test accommodation to learners with disabilities. So NAEP's goal, as we mentioned, is to assess what students in the United States can know and can do in mathematics, right? The standard time limit for a math test block is 30 minutes, meaning that if students take the standard version of the test, they receive 30 minutes. When your time is up, okay, you have to move on to the next block, right? Students with learning disabilities or English learners, they might be more impacted by test speediness. For example, they might have higher test anxiety, more likely to rapidly guess, or they might be more likely to have missingness due to running out of time, because not because they don't know math, but because they just need more time to be able to do the math, right? The extended time accommodation in this case would aim to help overcome the construct irrelevant nuisance due to lack of time, when speed is not an intended component of the test construct. So if you don't care about how fast the students solve math questions, but you just care about what they know and can do in mathematics, then the test speediness, or like all the things that happens because student is running out of time, it's something that's a nuisance that's irrelevant to what we care about, right? So as a result, the students with extended time accommodation, they actually receive the same test block, but with more time. So they are given a maximum of 90 minutes to do the same test block. So a lot of you are PhD students or instructors, and if you have T8 classes, you know that there are sometimes students who look for extended time accommodation requests, even beyond the NAEP exam. This has generated a lot of debates in the testing literature and among instructors. And one of the questions that a lot of people have is, does giving these specific students extra time indeed level the playing field and make the test more equitable? There are essentially two main considerations in this debate. The first is the effectiveness of the ETA, right? Which refers to, okay, you're giving the extra time and the ETA accommodation to these students. Is it actually helping them? Are they actually benefiting from it? The other aspect is related to validity, right? Which is, does ETA actually improve the performance for the students who use it, but not affect the students who don't use it? We're going to use the NAEP process data in this case study to mainly address the effectiveness aspect. In other words, we're interested in how does the extended time accommodation affect the behavior as well as the outcome in the math assessment for students with learning disabilities. I want to say that for those of you who still follow the news, you know that the NAEP exam is under some attack under the current administration about whether it's actually making meaningful contributions to our education, right? I want to make a strong argument for it using this case study here. That NAEP as a large-scale assessment that collects the process data provides a extremely rare opportunity for us to investigate this special group of students with a large enough sample size. And at the same time, it comes with the process data, which captures the students' interactivity with each question, which is something that we speculate to depend on time pressure. Okay, so let me introduce the data for this case study. The sample we have includes about 1,500 students with learning disabilities who took one of the blocks called the N03 block in the NAEP 2017 8th grade math assessment. So this is the same block of items as the screenshot I showed earlier, containing 15 math questions. So on the right side over here, I have a pie chart that describes the distribution of these students, which we characterize them into three subsets. The first subset is called not granted, or NG, and this consists of 39% of the students, and these were students who had learning disabilities, but they were not given the extended time accommodation. Why were they not giving it? Because their IEP didn't say they need it, so they didn't receive it. Okay. And then we have the orange group, which is 45% of these students with learning disabilities. This is called granted not used, or NU, and this refers to the students who were granted the extra time. So they can use a maximum of 90 minutes, but they didn't use it, meaning that they finished the block within 30 minutes. And then we have a last group, which is the blue group over here, which is only 16% of these students who were provided the extra time and actually used it. We call them granted and used, or U. So what you can notice over here is that, first of all, a lot of the students who were given the accommodation, they actually didn't take advantage of that, right? So the majority of them actually fall into this not used group. And in subsequent analysis, we're going to separate them from those who used the extra time. So people who used more than 30 minutes in the first analysis. Okay. So here's a description of the 15 items in this block. You can see that it includes multiple choice questions, constructed response questions, and also drag and drop questions. Here I provide a brief description of what each of the questions were. So for example, question 1 was related to translating a percent to a fraction. So I think it's like 25% is equivalent to, the correct answer is 1/4, right? Here you can also see the score range of the question. Some of the questions were dichotomous, where the maximum score was 1. So if the student is 0, they got it incorrect. If it's 1, they got it correct. But you can see that some of the questions, it's polytomous, and the maximum score was either 2 or 4. Right. I also show here the proportion of students who received the full score on the question. So this is just out of the students with learning disabilities, how many of them got the question correct, so completely correct. And you can see that some questions seem easier compared to others. Right. So what are the variables that we used in this analysis? The first thing we used was the ETA group membership. We already described that, which is for each of the 1,530 students, did they belong to the NG group, the U group, or the NU group, right? That's their ETA accommodation status. The outcome variable we studied was the score on each of the items, which ranges from 0 to the maximum score possible, right? It can be 1, 2, or 4. In addition, we will look at some of the process described variables on each of the item. And instead of working with raw process data, this study worked with predefined features that are conjectured to be associated with interactivity, which is the things like the time spent, the number of actions, revisits, and to use on the item, essentially things that capture how much interaction the student had with the question. To give you an example of some of the process features we work with, let's say this is a sample sequence we have. We have a student who entered the question, they turn on scratch work, drew something, turn off scratch work, chose the third option on the multiple choice, exited the question. For whatever reason, later on, they entered the question again and left without doing anything in between. So if you were to be given this sample sequence and you're asked to extract features from this sequence, so process-derived features, then these are some of the things that we can look at. The first one we'll look at is the number of actions, which is essentially the number of recorded events, right? What you have to do is just to count over here how many events are here. 1, 2, 3, 4, 5, 6, 7, 8. So this feature's value is going to be 8 for this particular student on this item. We can also count the number of visits. So let's say we care about page views of the students to this question that are longer than 3 seconds. Then we can see that the student entered the question twice. Let's suppose that both times they actually spend more than 3 questions, and then this value is going to be 2. Then we can extract some indicator variables of did they use drawing tool, did they use the text-to-speech tool. You can see that yes, they did use drawing, so this is going to be 1. They didn't use text-to-speech on this question, so that's going to be 0. You can also calculate the total response time in seconds, which is summed across visits for this student. Like say, if they spend like 60 seconds on the first visit and 42 seconds on the second visit, let's say the total time spent on this question is 102 seconds. One thing to note is that the number of actions and the response time were actually highly skewed. And in further analysis, we actually log transformed them. So they're less skewed. So if you download the files for this workshop, I actually provided you with a toy data set where you can play with some simulated data and play with some code that's provided to try to extract these expert-derived features of interactivity on your own. This data set is called toy.csv. Here's a screenshot of this data set. You can see it contains 3 columns. ID is the student ID, coding is the event, and time is essentially the timestamp in seconds. Right? So this data set is what I simulated based on the log data structure of one multiple choice question on the NAEP. And if you're interested in running the code that we described subsequently, it's also available in the section 2.rmd or markdown file. Right. But let's just look at the slides and look at the code over here and discuss how we generally can approach extracting these features. So expert-derived features in this case refers to some kind of pattern that based on our cognitive theory or educational theory that we believe to be relevant to whatever cognitive processes we want to examine in students' test taking. Right? Essentially, what we want to do is to look at the sequence data and see whether we can create some kind of variables based on the pattern that we want to search for over there. So we actually use a lot of regular expressions and the analysis of strings and characters in the analysis of these kind of process data and the extraction of expert-derived features. I provided a R source file called feature extraction functions.r, which by its name, you know that it includes a list of commonly used R functions for custom-derived feature extraction from the log data. And many of these are built on the tidyverse R package. For example, this is a function that's in this R source file that adds the visit index column to the log data we saw earlier, right? Essentially, it's going to count, so which visit is it for the student to this particular item. This function is called compute visit tool. It's going to take a data frame as its input that's similar to what we saw over here. And essentially, it's going to look at how many times the student has entered the question. Right? If this is the first time they do it, this is their visit number 1. If it's the second time we see enter item for this particular student, then it's visit number 2. Right? So it's going to, as an output, add a column to the earlier data that counts or indices which visit it is for this particular student. And there's a reason we care about that, which I'll describe very soon. You can see that here's an example. If you look at the first few rows of the output of this, you can see that this is the additional column of visit index. For this particular student, with ID 254, you can see that they only visited the question once, right? So all of these actions corresponded to visit number 1. But then for the student 492, they actually visited the question twice, right? Indicated by they actually entered the item at the later time point and exited again, right? So you can see that for the actions corresponding to their first visit, the visit index is 1. And then for the actions corresponding to their second visit, the corresponding visit is 2. The reason we care about this is this allows us to create some summaries or features at the visit level. So during this particular visit to the question, what did the student do? How much time the student spent, right? For example, we can look at a few things like the length of the action sequence during the visit, which essentially counts in addition to entering and exiting a question, which the student must do to be able to visit the question, right? What else did the student do? So it's going to count how many events additionally there is during this visit, as well as when did this visit start and when did this visit end, right? And based on the time start and time end, we can calculate the time between, which is the difference between these two, which tells us how many seconds the student spent during this particular visit to the question. We can create something called the visit summary out of this. And the resulting visit summary is going to look something like this data table over here, which you can see now we have the student ID like 1234444. So this particular student 4 visited the question 3 times, right? So we have one row for visit summary for each visit for student 4 on this particular item. And then here we can see that for student 4, during their first visit, they did one additional action. It's probably like clicking the choice on the multiple choice. We have their time start and time end for this visit, and the time between is about 30 seconds. The students during the second visit, they didn't do anything. They spent about just less than 2 seconds on this visit, so maybe they're just passing by, right? And then similarly for the third time, they didn't do anything, spent like 2.29 seconds, probably they're just passing by. So this is the kind of information we can summarize. And we can also use this to figure out which of these visits might be like cognitively meaningful and which of these might be just the student passing by, say they want to get from question 1 to question 3 and they're just passing by question 2 for like 2 seconds in between without doing anything over there. And we care less about those. Okay, so based on this, we can aggregate across visits for the subject to get some process-derived features for each subject. Things we can do include counting the number of visits to the question, called n visits over here. Essentially, it just counts like for each student how many visits there are. Right? And then we can also count the number of long visits, which I define here arbitrarily as the visits that had a duration of over 3 seconds. So you can imagine for the student 4 on the last page, their number of long visits is still going to be 1, although they visited a question 3 times. And we also can count the total number of actions across visits. as well as the total number of times and total amount of time spent on the question across the visits, which essentially is just summing up the time between the cross visits and summing up the number of actions or the length across the visits. The result of this will look something like the table on the right, where we have, again, one row for each particular subject. Right? You can see that subject 1 visited the question 1 time, had 1 visit longer than 3 seconds. Total time spent on the question was about 22 seconds, and the action they performed in addition to exit and entering was 1. Examinee number 4, what we saw earlier, they did 3 visits, but only 1 long visit. Total time spent is about 35 seconds, and the number of action is also 1. In addition to this, for this case study, we also created some binary features about whether an examinee used 2 types of tools that might be useful in solving this question. The first one was scratch work. This is indicated by whether they have draw in their action sequence or in the observable column that we saw earlier, right? So this is going to be just looking at, did they have draw? Yes or no? And this is going to return a 1 or 0. Similarly, text-to-speech. Did the student have some sort of text-to-speech event in their log data? Yes or no? And this is going to return a 1 or 0. And you can see that the results is going to look like this, for which it's a table where you have multiple rows, each row for a subject that indicates for this subject on this particular question, did they use scratch work? Did they use text-to-speech? And based on these, we see that for each subject, we have the information about these tool use. We also have information about like the visits, like number of long visits, total time, number of actions. Right? Let's combine these 2 data sets together using the left join and tidyverse to create a person summary where now we have all of the features we care about. Right? So for each subject, we're going to study these process-derived features in the study, which includes how many visits they had. So we're essentially looking at the number of long visit variable here, total times they spent on the item, number of actions performed on the item, their scratch work use, and text-to-speech use, which are 2 binary variables. Okay. So I do want to mention that there are other examples of commonly used functions for expert-derived features beyond what we show here. If you're curious about them, you can take a look at the feature extraction functions.r file and probably try to use some of the functions on the toy dataset I provided. For now, let's go back to the case study on the effect of ETA for LD students using these features that we discussed above. So we're interested in, is extended time accommodation changing something about these students with learning disabilities in their test taking, right? But we now have some features. Okay, that looks better than the original sequence data to analyze, but we still have some methodological considerations. First of all, ETA assignment is not randomized. As I indicated before, what determines whether a student receives extra time? It's their IEP, right? It's possible that some students receive, their IEP says they need extra time because they have more severe disabilities, right? So in the evaluation of the effect of extended time accommodation, this introduces a few potential confounds. First of all, there can be differences in the learning disability severity or the demographics for these students in these different groups. Well, there are things that we can try to do about this using some matching techniques, but for this particular study, we're just going to inspect these demographic variables across these 3 groups, just to get an idea about how much confound we're dealing with. Second of all, there can be differences in true math skill or knowledge for students, for these students, right? So maybe someone is going to say like, okay, you see the students who have extra time are not doing better, but is it possible that it's because those students with extra time, they started with worse math performance to begin with, like without time pressure, right? What we're going to do here is to do some kind of matching, essentially, intuitively, assuming that under any condition, there's minimal time pressure on the first 5 items in the test. we're going to test for the conditional independence between the ETA group membership and the score and interactivity on the remaining questions later in the test. So items 6 to 15, given comparable total score on the first 5 items. Intuitively, this means that we assume that whether you receive the extra time or not, when you're taking the first 5 questions on the test, you didn't feel too much time pressure. And whatever your performance is on those 5 questions is a true reflection of your math ability when you are not facing time pressure. And then we're going to test the effect of ETA on subsequent questions, score and interactivity, given that the student had similar performance on the first 5 questions when there's minimum time pressure. All right, so that's our first methodological consideration. The second is that the process features in this case for interactivity can have highly irregular distributions. So I talked about the log transformation we're going to do for the number of actions and the total response time, right? That's not going to solve all the questions. Your features are still probably going to be quite irregularly distributed, and it will be quite silly for you to assume that they follow some normal distribution and do some parametric testing, because very likely they don't. For example, some of the features in our case, like the number of visits to the question, can be what I call one-inflated. The idea is that there can be like maybe 90% of all of the students who just visit the question once, and then you have some additional 10% of students who visit the question more than once, and their count of visit is going to look something like it can go anywhere from 2 to infinity. So what we're going to do is, instead of adopting some parametric hypothesis testing that assumes specific distribution of these features, we're going to adopt a conditional permutation test for the conditional independence to circumvent the need of distributional assumptions. All right, so let's before moving on to the permutation test, let's look at the demographic differences across the 3 groups of students and see what kind of confounds we might be dealing with here. The 3 columns here, NU, U, and NG, corresponds to the not used, and not granted ETA groups that we mentioned before. I highlighted some of the things that we see are quite different across the groups. One thing you notice here is that for disability severity, we actually have a higher proportion of students with mild versus like moderate or profound disability in the not granted groups. So indeed, some students who are not given extra time, they might have learning disability, but it's mild, right? So there might be some disability severity differences here. We also see some differences if you look closer across demographic groups, but nothing that's particularly stands out. Now I'm going to talk a little bit about the permutation test. And the idea of it over here is very similar to the differential item function analysis, or diff analysis, we do in testing. We're going to treat the LD students without extended time accommodation, or the NG group, as our focal group. And we're going to treat the students with LD with the extra time, with ETA, either the U, the folks who used it, or the students who were granted or didn't use it as the reference group. And then based on the total score on the first 5 questions, we're going to divide the individuals into 4 strata, indicated by K over here. The maximum score possible on the first 5 questions was 7. So the scores possible on the first 5 questions in total can range from like 0 to 7. Right? We divide the students into those who receive a score of like 0 to 1 in total on the first 5 questions, 2 to 3, 4 to 5, and 6 to 7. In this case, testing the effect of ETA controlling for the performance on the 5 questions amounts to testing the following hypotheses over here, where H0 is the null hypothesis and H1 is the alternative hypothesis. Essentially here, the null hypothesis H0 says that the expected score Xi for the ith examinee across the focal and the reference group, given that they're from the cave strata, so they got this score on the first 5 questions, is the same for the focal and reference group across all of the strata. Translating that into human language, it means that if the students had a comparable performance on the first 5 questions, then regardless of whether they received the extended time or not, their expected score on the subsequent questions or like subsequent interactivity are the same. Right? The alternative hypothesis is otherwise, meaning that the ETA is doing something at least to one of those stratas, right? So here, xi stands for the features that we're working with or the score value of the student I, right? And si is the initial score strata for the student I, which is one of these 4 groups. You can note that here we're dealing with a one-sided hypothesis in our alternative hypothesis, which is the less than, right? Which in this case, we just care about one of the directions, which says that those students who receive ETA are higher on their expected score compared to those focal group folks, which are the individuals who didn't receive ETA. Okay, so here's the test statistic we use for the permutation test, and it's a stratified mean difference statistic. Essentially, you can see that it is a sum or a weighted sum across the strata from 1 to 4 of the mean score difference in the focal and the reference group in that strata, right? So here, WFK is the proportion of individuals ranging from 1 to 100% in strata K from the focal group or the students who didn't receive the ETA accommodation. Intuitively, the SMD here captures the overall item score or interactivity difference for LD students with and without ETA with comparable initial performance. Okay. Now I want to talk a little bit about the intuition of the permutation test. Intuitively, if the ETA or the extended time actually increases the score or interactivity on the later questions, the SMD should be sensitive to it and it should increase, right? So we'll see a larger SMD we saw on the last page, where the reference group individuals from the strata is doing better compared to those who didn't receive ETA. Right? However, if ETA doesn't matter, and another way we can put it is that we can randomly shuffle the group membership of the students. So it doesn't matter whether they are from the focal or the reference within the strata. So we can do this shuffle within the strata, so matching on the initial performance, and that shouldn't change the distribution of the statistic, right? Because the group membership doesn't matter. So let's suppose that on the left side is the observed data that we're originally dealing with. So we have students, a bunch of students. They're like SIs, which is their initial score on the question. So like student 1, 2, 3, 4 received a score between 0 and 1. Student 5, 6, 7, 8 received a score of 0, 2 to 3, etc. on the question. And group is which accommodation group they're from. Like, so some of them are from the NG group, so they were not given extra time. U is they were given and they actually took advantage of the extra time, right? And then this last column over here is their draw usage. So some of them used the draw usage, the drawing tool for scratch work, some of them didn't. So we can try to shuffle this data to create what we call like permuted versions of the original data. Right? The idea is that within the strata, so here within students 1 through 4, we can like randomly shuffle their group membership of whether they receive the accommodation or not. Right? Similarly, in the other strata, like total score 2 to 3, we can randomly shuffle their group membership. We don't shuffle anything else. And the essential idea is that we're going to calculate the SMD statistic on the unshuffled original data on the left, as well as like 1,000 copies of randomly shuffled within strata data that we create on the right. So there are like different ways that you can shuffle the group membership randomly, right? And say we have 1,000 copies of that, and on each copy, we can recalculate the SMD statistic using the like nonsense group membership. What you're going to do is to take the SMD you computed on the left side, which is the original data, compared to what you got, the 1,000 you got on the right side, like which is where group membership was randomly shuffled under the no assumption that the group membership doesn't matter within the strata, right? And this will allow us to see where the observed SMD lies within the 1,000 on like the permutation distribution under null hypothesis. And this will be allowing us to calculate some p-value, a one-sided p-value for the observed one, in terms of how likely it is to observe something that is less than or equal to the observed data, or like greater than or equal to the observed SMD value if our null hypothesis is true, where the ETA assignment actually doesn't matter. All right, so let's take a look at the results. First, let's take a look at the interactivity differences, which are some of those like process variables that we derived. Right? This table here compares, looks at the significance testing results using the permutation test on the last page, which compares the interactivity for those students who were granted the ETA and used it, and the students who were not granted, so who didn't have the extra time. You can see a lot of stars on this page, right? It indicates that we have a lot of results that are highly significant with p-value below 0.001. What this indicates is that across all of these like interactivity features like total response time, number of actions, etc., we see that there is higher expected response time and number of actions across almost all of these questions from question 6 to question 15, given comparable performance on the first 5 questions if the student was given extra time, right? What we also see is that there's a higher number of visits, percentage of students using digital drawing tools, and percent of students using the text-to-speech tool on select items, actually a majority of the questions, right? But if you look at the students who were granted the extra time, who had the 90 minutes but didn't use it, which are the end-use students, and you compare them to the students who are not given the extra time, there are much fewer stars on this page, right? Which indicates that we can see that here there's higher expected response time, number of actions, and number of visits on the last few items for these students. Otherwise, there's no difference in interactivity for the students who are given, who are not given ETA. But we also care about the scores, right? So when we say is ETA helping the students, we not only care about are they doing more things on these questions, we also care about when they do more things, are they actually doing better, right? So here are the results of doing the permutation test when our outcome variable is the final score on questions 6 to 15. Even if you look at the students who were granted and actually took advantage of the extra time, you see there are much less stars on this page, right? There are only like 1, 2, 3, 4 of them where the p-value was between 0.01 and 0.05. And you should also take into account that you're doing multiple testing over here. So overall, you will have some sort of type 1 error inflation, right? So essentially, we found that over here, for those students who used the extra time, yes, they did more things across almost all of the questions, but their expected score was only higher on items 6, 9, 11, and 13 over here. So here what we showed are the test statistics, right? Subsequently, there will be some speculation about why is it these 4 specific questions where the students who were given the extra time were doing better. So this is purely speculative, but I'll present to you what I think is happening here. Here's a plot of questions 6 to 15 on 2 variables. The orange bars is for each of the questions, the median response time for the students who were not granted extra time with a non-zero score. In other words, for students to get some score on the question, what was the median score, median response time they spent on the question? The blue curve over here is the proportion of students who received the full score on this question. So you see that it ranges from 0% to 100%, and essentially it's a surrogate for item difficulty or easiness, right? You can see that question 9 and question 6, they look pretty easy, right? The proportion of the student getting a full score is quite high. And question 11 and 13 actually had the highest median response time if you wanted to get some score, right? All right, so here's what I think was happening. If we look at one of these questions, like item 13 over here, so this is what the question looked like. I want you to recall like item 8 that we saw earlier, which was that question, like multiple choice question we showed at the very beginning that involved the rotation of a triangle. If you compare question 13 here to that question, what you notice is that this question looks a lot more time intensive, right? This is a statistics question, and you can read the question. It says that a teacher surveyed 8 students in a class and found out that what kind of like animals they have as pets. Two students, they drew some figures based on the survey results. Here's a pie chart of this, and here's a corresponding bar graph. First part of the question asks the student to see, based on the graphs here, which of the following sets of data could be the results of the survey, right? And you select all of them, that applies, right? Second part of the question, you're going to try to use this and this figure together and try to like fill in the blank over here and say what are some possible data that comes out of these. So my feeling when seeing this question is that it's not extremely difficult, but for the student to get some score, they have to spend a long time reading this question and to figure out, probably enumerating each of these possibilities in the options to figure out which one is possible and which one is not possible based on these two charts over here, right? So this will be one of those questions that's probably not too hard, but actually demands some time to be able to get some score. All right, so going back to the conclusions we have for the first case. So how's the ETA affecting the LD students' interactivity and score? First of all, we saw that many students with LD who were granted EDA did not use it, and they didn't do any better, right? Second, given comparable performance on the first 5 questions, those who used the extra time interacted more with later items compared to those without ETA. And this was indicated by spending more time, having more log actions, using more tools, and also made more revisits to the same question, right? In terms of performance, if we assume that the performance on the first 5 questions is an accurate reflection of the students' know and can do in 8th grade math, then given the same proficiency, those students who were given and used ETA could actually benefit from the extra time on some specific questions. And my personal speculation is that these are the questions where they have the skills or knowledge to partially solve them if they had sufficient time. However, if they're under like test speediness and they're running out of time, they might know how to solve it, but they don't benefit. They don't actually solve it correctly. Our paper actually contains more findings. So I talked about one of the limitations, which is the disability severity and some of the demographic differences that can be confounding the results. So in the paper, we also apply quasi-experimental methods, such as propensity score weighting, to examine the effect of ETA usage when we control for those potential confounds. In addition, we look at some affective and non-cognitive variables, like the effect of EDA beyond the interactivity and item performance, such as the students' test-taking experience reported in the survey. And it turns out that the students who were granted the extra time, they actually felt better taking the test as well. But I want to move on to study 2, which is related to using some of the data-driven features. And this one is going to be related to one specific question. This is a paper that's conditionally accepted to Psychometrica by my student Sunbom Kwong at UIUC and me. And this is related to the explaining performance gaps using latent class mediation analysis. So we want to look in this context beyond summary statistics. For example, are the log data from a open-ended or constructed response question, which I call CR items over here. Many of the prior studies have separately examined group differences in process patterns, as well as process pattern differences for students who successfully solve a question versus students who get it incorrect, right? But if you want to draw a generic claim about what kind of process patterns may be explaining the group differences in the final responses, it actually requires a single coherent model, right? I'll present some of the empirical results from a latent class mediation analysis, or LCMA, on one single constructed response question. I'll give you a sneak peek to the results over here. So it turns out that on this particular question, the distribution of misconceptions resulting in a wrong response for the general population appeared to be different from that for the students with learning disabilities. So here's the question. It looks very simple. 4.9 times 1.5 equals what? Right. It's a fill in the blank question, so the student can type their numerical answers in this space over here. And on this question, we'll have the keystrokes for the open-ended response, their tool usage, as well as the visits and revisits. So for this question, we're going to extract some data-driven features using multidimensional scaling, or MDS. This is a method that's used to transform variable length action sequences into k-dimensional continuous features, which I denote by mi over here, by finding the m's for examinee 1 through large n, the total number of examinees we have, that minimizes this objective over here. In this objective, dii prime is the dissimilarity between si and si prime, which is the examinee i's sequence on this question and examinee I prime's sequence on this question. This is computed based on some kind of order-based sequence similarity metric, which captures like how dissimilar the two sequences are for these two examinees solving the same question. Some notes about the MDS features here. First of all, they often very accurately predict final scores on the questions, which means that the process features in a lot of empirical studies actually capture the original sequence information, including whether the student get the answer correctly. Second, they are dense numerical features that by themselves lack inherent interpretability. In other words, you have no idea what they actually mean without doing some further analysis. K, which is the dimension of it, is usually chosen based on cross-validation. And intuitively, the MDS features over here, based on this objective, you can see that it's taking the square deviation. We want to minimize the difference between the original sequence dissimilarity, so dii prime, and this thing over here, which is the distance, the Euclidean distance between mi and mi prime, which are the features we extract from the original sequences for the two examinees. If these two are as similar as possible, that essentially means that the features m's preserves the pairwise individual differences of dii primes in the original sequences. So what is the dissimilarity metric we use over here? The dii prime. The formula is given here, but I just want to provide you some general intuitions. Essentially, this dissimilarity depends on two things, the blue part and the orange part. The blue part here essentially looks into how much difference there is in the ordering of actions that both of the examinees did on the question. So let's suppose that both of them type something like 7 on this question. Then we'll look at where did you type 7 and where did you type 7. If the ordering are very similar, and then this f is going to be small, close to 0. But if, like, say, this examinee types 7 very early and that examinee types 7 like the 100th action in the sequence, and it's going to be large. The other part is the green, the orange part, G. This essentially looks into the similarity in terms of the number of unique actions. So when we say how different are two examinees sequences, we can look at so how different are they in terms of things that both of them did in terms of ordering. Right? You can also look at what are the things that one of them did but the other person didn't do, and what are the type of things that the other person did that this person didn't do. So that's going to go into the orange part. So if you have two examinees, they did very similar actions, say exactly the same actions on the questions, and the ordering of those actions are also exactly the same. The dii prime over here is going to be equal to 0, means that the sequences are completely the same. That means that they are super similar. Right? Otherwise, the dii prime is going to be larger. If you want to run the code, I included that in the R Markdown file. And this MDS-based feature extraction was actually implemented in one of the R packages that my collaborator Xueying Tang developed with us. So this is using a package called the proc data. And in order to use this package to extract process data, what we first need to do is to create something called a proc object that we use for this analysis. Essentially, we just first need to split the data, the original log data we saw earlier, that CSV file, based on subjects. So you see that each element in this list over here is going to be one examinee's sequence of actions on this question and the associated timestamps. And then we are going to find out what are the action sequences and the time sequences. Essentially, just for each subject, you look at what is the coding column, right? The actions, and the corresponding timestamps for these actions, right? So if you look at these, you can create something which is a list of all examinees' action sequences. So each of these is for one examinee. And then for each of them the corresponding timestamps for these sections. To create the proc objects, you just do like the log file proc object is going to be proc, where this is the action sequence and here's the time sequence that we just created for these examinees. Right? The outcome of it is going to look something like this, which is a proc object. If you look at the first 3 examinees, essentially we have for examinee 1, here are their first 3 steps: enter, choose 1, exit, and the corresponding timestamps. And then for examinee 2, etc. There's a function in the proc data package which takes the proc object we just created as the input, which is essentially the process data for the examinees, right? And it's going to return you the multidimensional scaling features that we extract. For example, if you want to say extract 5-dimensional features, MDS features, from the log data, the toy data, you can call this function called seek to feature MDS, plug in the log file we just created, the proc project, say that we want 5-dimensional features, and here's the result you get, MDS feeds. There's going to be an object called theta. Theta is going to be this 5-dimensional, 5-column matrix, where each row is going to be one of the examinees where we had the process data. Right? Each column is going to be one of the dimensions of the process data. What you can see over here is we have 5 dimensions. The MDS features, what do they mean? We have no idea, but these features now are numerical. Hopefully they capture the original sequence information, but in order to make sense of what exactly is captured, we need to do something else with them. So in the proc data R package, there are actually other arguments that can be supplied to MDS feature extraction, as well as other kinds of feature extraction methods like n-grams that Qiwei has talked about, and sequence-to-sequence autoencoders based on neural networks. But for now, let's return back to the case study on trying to understand, can we study the constructor response questions process to understand why the students with disabilities are doing worse compared to their peers on this question compared, All right, if we look at the final outcome on this question, 4.9 times 1.5. Right? On this question, the student with learning disability did remarkably worse compared to their typically developing peers, their TD peers. So about 21% of students with LD answered this question correctly. About 48% of their TD peers got this question correctly. If we do a logistic regression, regressing the final score, correct or incorrect, call it Y over here, onto the group membership, where G is equal to 1 or 0. 1 is learning disability, 0 is the student is typically developing. And we can see that we get a slope and an intercept in the logistic regression. The slope we have is about negative 1.19. And if we study the direct effect of G on Y, which is the expected score difference for these 2 groups of examinees, we get negative 0.27, right? Indicating that the expected score of the 2 groups is about like 0.27 difference. Right. The action sequence data affords us an opportunity to explain the achievement gap by uncovering the differences in test-taking process that lead to the difference in performance between the 2 groups. And here's the intuition behind it. The action sequences, which are probably captured, so the sequential patterns are captured by the MDS features. It can include things like the specific keystrokes, like what did the student type as the answers, whether they use something on the calculator, if possible, whether they did use some kind of tools like scratch work. They might partially explain how the student arrived at a final right or wrong answer. And students who have different sequential patterns might get different scores. That's very natural. There might be common sequence patterns associated with a higher score. There might be common sequence patterns that are associated with a lower score. How do we find common sequence patterns? We can do it by clustering, or we can do a model-based way using, say, latent class analysis. We see over here already that TD and LD students differ in their final score distribution. Then what we care about here using process data is, can we try to explain this final score difference by the differences in sequential patterns? For example, are LD students more or less likely to demonstrate specific kinds of sequential patterns in solving this question, which is shown in their process data, which resulted in a lower chance of correct response? The LCMA is going to serve three goals. First of all, to identify latent classes for test-taking sequential patterns underlying the distribution of process features. It's going to also find a set of process features that best explain the effect of observed group memberships on the outcome. In addition, it also will be able to assess the indirect effect of group membership on the outcome through the nominal latent class mediator, which is the patterns of test-taking process. Here's a graph summary of what the model looks like. Essentially, here the omegas ranging from 1 through L are the latent class membership for the test-taking process. So here we can see that essentially these are the latent classes. Each student falls into one class, and that class determines like what kind of sequence pattern they have. And of course, that dominates what kind of like values they get on the MDS features, M1 through MK, right? G and Y over here is the grouping variable, LD or TD. Y is 0 or 1, correct or incorrect response. Right. This model assumes that the relationship between G and Y, which is the group difference in the final score, is mediated by omega, which is the latent class underlying problem-solving process patterns. So here, I'll just briefly go over some of the model assumptions. Of course, you can read it in the paper. Essentially assume that underlying different latent classes, the distribution of the process features are different with group-specific means and covariances. Situatively, it says that different clusters of examinees demonstrate different kinds of sequential patterns. This arrow over here is for capturing what is the group membership's effects on the problem-solving patterns. Essentially here, we're assuming that it's possible that the LD students may be more or less likely to demonstrate specific kinds of test-taking process patterns, which make them more or less likely to fall into specific ones of the L classes in that omega. And this last one over here describes how is the final score Y related to G and omega. In other words, how different test-taking sequence patterns, which is omegas, can imply different chances of correct response. But some of that can still depend on the G, which is the group membership, that cannot be explained by the process patterns. Okay, we did mention one issue with process feature, which is they are high-dimensional and noisy. Right? For this study, we used cross-validation and selected 20-dimensional MDS features. As you can imagine, some of them might be irrelevant to the empirical question we studied. We want to find some interpretable results to explain this group difference in the final score. In other words, we want to select the most relevant sequence features in this context. Right? We did a variable selection, and our objective is not to maximize prediction accuracy of anything, but instead we want to maximize the total indirect effect of the latent class mediator explaining this group difference. So if we use this thing, so E of YG omega G prime, to denote the expected outcome Y in group G, given that the latent class mediator omega is held constant at the value it would obtain for group G prime. So G and G prime can be the same group or different groups. Okay. Then the total indirect effect is defined by this expected value difference over here. Long formula, the intuition is that this thing is going to tell us for students with learning disability, if the distribution of their latent class omega for problem-solving process patterns flips to that distribution for the TD students, how much does their expected score change? Okay, I want to quickly present the empirical results. Here we use a data set that contain both LD students and the students who are typically developing. So we had about 3,000 students who took this math question who were not given the extended time. About 590 students of them or G equals to 1 were students with learning disability. Of course, the remaining 2,500 were the typically developing students with G equals to 0. Out of these 3,000 something students, about 1,300 of them answered this question correctly with Y equals to 1. The remaining students got this question wrong. Using the variable selection approach I discussed on the last page, we selected a total of 5 process features out of 20 that were relevant in explaining this group difference. And using these 5 process features, we found a total of 6 latent classes of problem-solving patterns. Without the latent class mediators, we recall that the direct effect of disability membership on Y was about -0.27, right? after incorporating the omega, the latent class mediator of problem-solving process, we saw a substantial decline of the direct effect to about -0.06. It's not 0 yet, but it's much smaller. Right? The total indirect effect of the latent class mediator in explaining the group difference in the score is about -0.21, right, with the following 95% confidence interval, which means that the latent class for test-taking process partially explained the relationship between disability group membership and the final score. Now I'm going to quickly present some interpretations of the results. So here are the 6 latent classes and what I think, based on looking at their process patterns, these classes mean. So these are 6 classes of students, right? Each of them, they had their problem-solving process. We can go back to their log data to see what are some patterns in each of these clusters. First class is what I label correct with no tools. These are the students who didn't use any of the tools but got the question correct. Second class, incorrect with no tools. Didn't use tools, got the question incorrect. Third class, 100% of them use scratch work on this question. Oh, by the way, this question didn't allow the students to use calculator, so they better use scratch work to be able to figure out what is the answer of the multiplication. Class 4 is what I call irregular tools, which is the usage of things like theme change equations when this question just involves like digits, and things like text-to-speech. So things other than scratch work that were used on this question. Class 5 is called revisit, and you can see that the majority of students, they revisited the question, meaning that they visited the question more than once. And then class 6 is called wrong decimal point, which featured one type of incorrect answer. That's called 73.5. So for this question, it's 4.9 times 1.5. Correct answer is 7.35. If we look at the most common responses and the proportion of each class, of course, class 1, 100% of them got the correct answer of 7.35. That class 6 I talked about earlier, 100% of those students got the answer of 73.5. You can see what the error was, right? The student did everything correct, but they put the decimal point at the wrong place. So that was what class 6 was referring to. But if you look at some of the other classes and the answers, you see that there are some more creative answers. For example, in class 2, what was this 8.5 and 4.45 about? And how did the student got all of these answers? Let's try to look at the LDT difference in this. And here are a few observations we can make. First of all, if we compare class 1 and class 2, we can see that when we don't rely on any tools, the LD students were more likely to get the question incorrect compared to the TD students. If we look at these two columns here, the probability of correct response for these two classes. There are much more, if we're not using tools, there are much more like TD students in this class, who are correct, and then a lot of LD students were incorrect. If we look at class 3, you can see that scratch work actually helped both LD and TD students achieve higher than overall correct rate. So in class 3, 29% of LD students got the question correct. That's higher than the marginal correct rate of 21%, and about 52% rather than 48% of TD students got this question correct. If we look at class 4, LD students were more likely to be in this particular class, like 26% of them were in this class. So this is like browsing and trying tools other than scratch work, and this class was also associated with relatively low correct response probability around 0. So whoever were belonging to this class, they didn't get the question correctly usually. Looking at class 5, we can see that TD students were slightly more likely to be revisiting the question, and these were students who actually 100% of them got the question correct, right? So we're probably checking the answers, and that actually makes them getting correct answers. If you look at class 6, you can see that there's actually a slightly higher proportion of TD students who were in this class compared to LD. If you compare this to class 2, which are two classes of incorrect responses, but different kinds of incorrect responses, surprisingly, the TD students were slightly more likely to submit the common incorrect response of 73.5 due to the decimal point error. And now these students actually featured more of these like creative incorrect answers. Right? Some implications for intervention of this. So first of all, If we just look at the absolute value of the total indirect effect, it tells us how much score gain we can expect for LD students if their test taking patterns can be intervened to be distributed instead like their TD peers. If we look at tool usage, we see that the correct rates on classes 1 through 5 suggest that various tools and universal defined feature usage contributed to the performance on this question differently. Scratch work was useful, right? And actually associated with higher score for both classes of students. The usage of other tools like text-to-speech on this question, I'm not sure what the students were reading on this question out, then they actually were constituted latent classes with lower correct response rate, right? So maybe there can be interventions targeting how to effectively apply specific tools to different types of problems, and that can help shift LD students into latent classes who use the more helpful tools who are associated with higher performance. Right? Another thing we found was some incorrect answer response differences in the two classes for this question. Right? The LD students more frequently were more likely to be in class 2, which you can see featured these other incorrect responses like 8.5, 4.45, etc. So I was curious what these answers were referring to and eventually figure out what they were doing. So the original question was 4.9 times 1.5, right? If the student thinks that to do decimal multiplication, you can just multiply whatever is on the left side for the two numbers, multiply whatever is on the right side of the two numbers, and then shove them together. And then they will get 4 times 1 equals 4. 9 times 5 equals 45. And if they combine them, can either be 4.45 or 8.5, which is 4 plus 4.5. So LD students were more frequently showing these conceptual misunderstandings about decimal multiplication beyond the common misconception of placing the decimal point in the wrong place, right? And in this case, maybe they're getting the question wrong in like more severe ways, and they deserve like interventions that actually look into these conceptual mistakes. Okay, so this wraps up my presentation, and I would like to acknowledge the grant that supported our research and also this amazing data set that supported this. Thank you.